Okay, so this is the fifth exercise in the diagram windows course, and in this exercise we're going to use some of the stuff that we've just got done talking about in some of the previous videos. Specifically maybe putting in some links in the window, and then also having some RTF objects as well as a table. So this is the problem we're going to do. So it's down here you can see a picture of an experiment that's meant to determine the heat transfer coefficient for an internal flow. So you have an internal flow of, in this case it's water at atmospheric pressure, going through this test facility. The test facility measures the mass flow rate. It measures the heat transfer rate going to this copper sleeve, which then goes to the water, and it measures the inlet and outlet temperature of the water as well as the wall temperature of the copper sleeve. So the copper is meant to give it a constant wall temperature. You can see the diameter and length are indicated as well. So what you need to do is provide a link on the window that allows the user to load up a lookup table that contains a column for each of these measured variables: mass flow rate, inlet, outlet, and wall temperature, and heat transfer rate. The user should also be able to enter the uncertainty on the window for each of these measured variables. And then what you'll do is, for every row in the table, you'll go through and calculate the heat transfer coefficient, and you do this using the log mean temperature difference equation here, and then non-dimensionalize the heat transfer coefficient as a Nusselt number, and then plot the Nusselt number as a function of Reynolds number, which is given here. And then each data point should have an error bar on that plot based on your uncertainties. And then finally put a rich text formatted object in the window that discusses the result, and a table that delineates the various sources of error for the last data point in the lookup table. So go ahead and give that a shot, and then we will go through this exercise. This tends to make a very long video, but I'll put links, segments in the bottom, bookmarks that you can use to navigate through it to get to the parts that maybe you got stuck on. But yeah, that's the exercise. Okay, so let's get started with this. I think the first thing I'm going to do is specify that the unit systems are going to be in base SI units. So dollar unit system, SI, mass, joules, Kelvin. Actually, let's use Celsius, Pascal. That's just because I know I'm going to have to get some properties for water to calculate the Reynolds number and the Prandtl number. Let's also specify, at least initially, the data file that we're going to use. So select file $ equals data.lkt. So this is the data file that I have set up on my computer that has the mass flow rate, heat transfer rate, and the temperatures in it. Eventually we'll put a link on the diagram window that will allow the user to navigate towards whatever data file they're interested in. What else do we got to put on here? Maybe we'll put on here the uncertainties. So the uncertainty in temperature, maybe 1.5 Kelvin. The uncertainty in mass flow rate, so I don't know, 0.001 kilograms per second. And the uncertainty in heat transfer rate, which is maybe 100 watts. Again, those will be specified eventually by the user on the diagram window. So the next thing maybe is some of the known values. So the diameter is 0.115 inches. So we should probably convert that to meters. The length is, I think, 6 inches. And we'll convert that to meters as well. The fluid is water, and the pressure is atmospheric pressure. So that should all work. Alright, so at this point everything seems okay. I think probably the next thing to do is get the data. So let's do this for the first run. So let's just maybe say table run equals 1, and m dot then is, what are we going to do? We're going to get the data out of the table. So we'll use the lookup function. The lookup function takes 3 arguments. The first is what's the table. So this is a table that's on the hard drive, but it's still a lookup table. The second is what's the row. So we're just going to do this for the first run, at least at this point. And then what's the column. So there's a column named m dot. So let's just make sure this works. Yeah, so that's the first mass flow rate in my first row. So we'll copy this and get the other things that we need, which are what I think I need, the heat transfer rate. So q dot. So we'll turn this to q dot, and then I need my 3 temperatures. So Tn is in the column Tn. Tout is in the column Tout. And then finally T-wall is in a column called T-wall. So let's run that, and everything looks good. We'll go ahead and accept these units. So Control all, and then if I just said OK, you can see that all these units have been accepted. Okay, so far so good. I think what we're supposed to do with these data is, first of all, calculate the heat transfer coefficient. So Q dot is equal to h bar times pi times d times L, that's the area, times the log mean temperature difference, which is T out minus T in divided by the natural log of T wall minus T in divided by T wall minus T out. I think that's right. If I want to look at this and make sure that I have that equation right, I can look at it in formatted equations window, and it looks like I got that right. This is handy sometimes for equations like this with fractions and multiple things in the denominator and the numerator. So the heat transfer rate then is right here, and that should be in watts per meter squared Kelvin, and that looks good. Okay. I think the last thing that I'm supposed to do here for calculations is figure out the Nusselt number and the Reynolds number, and to do that I'm going to need some properties. So let's go ahead and get the density of my fluid at T equals T. So I should probably use the average temperature, so I'll calculate that here in a second, and P equals P. So the average temperature of the fluid is T out plus T in divided by 2. Alright. What else would I need here? I need the viscosity, so mu. And I think I need the thermal conductivity, so K. Like that. And that should be it for properties. Let's go accept these units. So Control all, and then OK. So that all looks good. Maybe save. So let's call this exercise 5 solution. Alright. And then finally I need to calculate the Reynolds number, which requires that I know the velocity. So I'll get the area of the tube, so pi times d squared divided by 4, and then u is the mass flow rate divided by the density times the area. And the Reynolds number is rho times u times d over mu, and the Nusselt number, I guess it's the average Nusselt number, is h bar times d over k. And we should check that. Everything looks good. Dimensionless. This is units of meters per second, and that has units of meters squared. Now let's save. So at this point everything looks pretty good. I think maybe what's the next thing we should do? We have 8 rows in our data table, so I'm going to make a parametric table that has 8 rows in it, so that I can process basically every one of my data tables. So here, tables, new parametric table, 8 rows. I can put whatever I want in here, but I definitely want the table run, and I want the Nusselt number, and somewhere I want the Reynolds number. So we'll put those guys in there, and we will run table run from 1 to 8 like that. And if I run this table, well, first I have to maybe put this in a dollar if not parametric, dollar and if. Let's indent and give myself a space. So now if I run the table, so tables, calculate solve table, yeah, I have the Nusselt number and Reynolds number for every single data point. Alright, so the program asks that we calculate the uncertainty of these guys, so I'm going to have to run an uncertainty table, and to do that I'm going to go here to calculate, and then uncertainty propagation, not just for one point but for the entire table, like that. And it's going to ask what are your calculated variables, and these are both calculated variables, and then what variables have uncertainty, and we are going to apply some uncertainty to m dot, q dot, and then all of these temperatures. So I'll hit set uncertainty, and the absolute uncertainty is given by these variables that eventually the user can enter. These are all dt, dt, and dt, and we'll hit OK, and we'll hit OK, and yeah, you can see that now not only do I have Nusselt number, Reynolds number, I also have their uncertainty. And let's see, what else should we do here before we go to the diagram window? One thing we can do is make a plot and actually maybe put the directive in here so that the plot is automatically updated. So here I'll go to new plot window, and I want to plot, looks like Reynolds number on the x-axis and Nusselt number on the y-axis, and we definitely want to show some error bars. I don't think we want lines, and we want to add that directive, so we'll call that plot 1. That seems okay. There it is, plot 1. And here is the directive that will make sure that we in this case we will replace plot 1 with a new plot every time we run this. So if I change something, I don't know, I can change this to 2.5 and run the uncertainty propagation again, and go look at our plot. You can see that it's changed. Now the error bars are bigger, and in this case they're shaded. I think the last thing I probably want to do, given that I want to have a table in the diagram window that delineates the various sources of uncertainty, is get those various sources of uncertainty. So I can get that with I think it's uncertainty of, or percent uncertainty. I'll go to function information and figure this out. Let's see. So if I go all the way down to the bottom, yeah, uncert.percent, and that will give me the percent uncertainty in x that is due to y. So here, for example, we might get the percent uncertainty in the Nusselt number that is due to the inlet temperature or something like that. So let's go ahead and paste that in. So we will do, I don't know, percent, let's say Tn, like that. And this will be the percent uncertainty in the Nusselt number that is due to T in, like that. So let's go ahead and copy this, I guess 4 more times, 3, 4. So we'll have the same thing for T out, T wall, M dot, and then finally Q dot. So over here I got to change these as well. So T out, T wall, M dot, and Q dot. And at this point, I think think if I press F7, which is the shortcut key for doing uncertainty propagation table, I have my plot, I have my table, and if I go to my solutions window, I have each of these percent uncertainties. These should all be in percent. So this is percent. It's 0 for mass flow rate because mass flow rate is not used in the calculation of the Nusselt number. That should be percent for Q, percent for T wall, percent for T out, and then finally percent for T in. And yeah, I think at this point we'll save. My calculations are done, and now all I have to do is sort of transfer this stuff to the diagram window and make it look nice there. So yeah, let's go ahead and go to the diagram window right here. I think the first thing I'm going to do on the diagram window is add a picture, right? So one of these is add a picture. So here's add a picture, and let's go ahead, and if I click in the file name, I think I can navigate to my picture. Here's my figure. There it is. Maybe I want to make it a little bigger, but there's my picture. And probably I'll go ahead and have inputs here for the uncertainty and all these quantities. I can put them right here on this picture. So input for dm dot. Yeah, I think I want to include the variable name, so the units. We'll put that up here. We'll add an input for dq dot, and maybe move that up here. Oh, I overwrote my dm dot. Let's put that back on again. What else do I need? Tn, so an input for Tn, or dTn, I guess, the uncertainty in Tn. So where is that? They're all the same, dt, so we'll put that here. I guess we'll just put that down here. So there's my 3 uncertainties that I've entered. If I'm going to enter here on the diagram window, I probably should go back to the equations window and put all of this stuff, dollar if not diagram window, and then down here dollar end if. So I think at this point it should still run. Let's see. Yeah, still seems to work okay. Everything's good. Alright, what else do I need here? I need a link that will let me navigate to the table. So let's see, I'll go down here to links. Where is that? Right here. And we want open lookup table link right here. And I think I called it select file. So I'm going to call my caption select file here and hit OK. And yeah, I'll put that right there. And now let's go back to the equations window, and we'll put this in the dollar if not diagram window clause, because now I'm going to actually use my link to set that. So if I put myself in development mode and click here on select file, there's my data table. I'll click on that, and what should happen now if I go to the solutions window, actually I guess I have to run first, is you should see that the solutions window, you should see that the name of the caption, so select file $, is assigned to the value of the lookup table that I just opened, or the user of the program just opened. So now if I click to a different data table, a different lookup table, this would change, and I would be processing the data in that file instead of this file. Okay, so let's see. Let's go back here. The other thing I probably want to do is give myself a button to initiate those calculations. So here's a calculation button. I'll put that right there. I don't want to solve. I want to go all the way down here and do an uncertainty table like that. And maybe we'll just do calculate uncertainties like that. And probably I gotta make it a little bigger, so maybe 350, like that. Okay, so that looks pretty good. I am supposed to put that plot on the window, so that's pretty easy. I'll go ahead and click the show plot button. I don't want to add a button to link to the plot. I actually want to show the plot on the window, so I'll hit OK. Let's move this down here out of the way. I want to add a rich text format that maybe talks a little bit about what's going on here and has a live variable telling you what the Nusselt number is. So here, formatted text. What do we want to say? The Nusselt number is calculated for each data point. Let's see, the Nusselt number for the last data point is, and we'll just put XXX just now, at Reynolds number YYY. See the graph for Nusselt versus Reynolds and the table for a delineation of uncertainty. I don't know, something like that. I'll hit OK, and you can see we have this this RTF now, which I can resize. Maybe I'll, oops, I want to resize it. So I'll grab this handle here and make it narrower, and we'll move it over here. And then I'm going to take this XXX and get rid of it. I guess I'll replace it with a variable, so insert variable. Let's see, I want Nusselt bar. I don't think I want the name. I'll hit OK. And then here, I'm going to replace the YYY with insert variable. Go down here and select Reynolds number, get rid of the name. And if I go to development mode, yeah, they've been replaced by the 257, and the Reynolds number is 39114, which is, yeah, right about correct for this last data point. Okay, the last thing I'm going to do is put a table in here. So insert table is this button right here. I guess I want, let's see, there's 5 sources of uncertainty, so maybe 6 rows, so I can have a header, and we only need 2 columns, and yeah, I don't know, 150, maybe center the alignment, and hit OK. There's my table, which I think I'm going to go ahead and bring down here, and this will be a source of uncertainty, and then the percent of the uncertainty, and this is for the Nusselt number. So this is I guess a T wall, a T in, T out, Q dot, and M dot, like that. And here I'll just put those variables. So let's see, this is T wall, so I want percent T wall right here. Maybe don't put the name, put the units. And I think I'll just copy this if I can and paste it in each of these cells and just change the variable. So this is not T wall, this is T in. This is, I guess, T out. This must be Q dot, and this is M dot. And yeah, if I go to development mode, these are the percents. I guess it makes sense. So at this point, I think it's working. If I want to change the file, I can navigate to a new file. If I want to change these uncertainties, I could do that. So maybe I want to change the, I don't know, let's change the uncertainty and temperature back to 1.5 and run through the table. And you can see the error bars got a little bit narrower, and these percents didn't change much. Let's see, maybe if I make this bigger, 200, maybe let's just go 300, which is really big, I guess. But We'll go through that. Yeah, so the error bars got bigger, and certainly a larger percent of the uncertainty is due to QDOT. And I think that concludes this exercise.